Hello everyone and welcome to another solutions video today for round 762 division 3. Yeah, that's right. I'm leaving the contest midway to make solutions just for you people. Yeah, who am I kidding? I'm making it for my own views. I'll get more views if I post it just after the contest. So let's begin. Problem A, square string. So in this problem we are given a string, so it can be anything, A, B, C, D, A, B, C, D. And what we want to tell is that if it is a square string or not. What is a square string? A string which is repeated twice. So here, as you can see, string ABC ABC or string BAA BAA. Since the first half is equals to the second half, it is a square string. So how to check if something is a square string? Obviously, first of all, it has to be of even length because odd cannot be divided into two, and I mean equally divided into two. And then we want to check that zeroth element is equal to the fourth element, first element is equals to the fifth, sixth equals to second equals to sixth, and third equals to seventh. So as you can see, we want to check I is equals to I plus n by 2 for every I belonging to 0 to n by 2. So that is the simple solution. You can have a look at the implementation. It is trivial, obviously. So I take an input string and then I calculate n. If it is odd, obviously I cannot do it. Otherwise, I iterate from 0 to less than n by 2, and I want I to, and if I is not equals to I plus n by 2, then no, otherwise yes, because it has to be equal at all places. If it is not equal at even one place, I return false or print no. So second problem now, problem B, squares and cubes. So in this problem, we are given a number n. Okay, let me use black color. So we have a number n and we want to find all the numbers from 1 2 3 up to n such that they are either a perfect square or a perfect cube. So as you can see, 1 4 8 9, we want to see as you can see, both all of them are either perfect square or perfect cube, or they can be both perfect square and perfect cube, like 1 and 64. 64 is a square of 8 and cube of 4. So we want to find the distinct values, the number of distinct values. Okay, so how do we go about doing this? Well, as you can see, n is 1e9 and test case is only 20. So what can this imply? Well, we will look at it later. But first of all, notice that you want to find all the perfect squares, and to find all the perfect squares, how many perfect squares will be there up to n? 1 4 9 16 up to something, and then which are less than equals to n, right? So this is some last value, k times k. Okay, and k can be equals to n if n is a perfect square, sorry, a square root of n. So these will be the perfect squares less than equals to kn, and as you can see, they are increasing obviously in the square fashion. So k has to be less than equals to square root of n, right? So we can just find all the unique values by using a for loop from 1 to square root of n, and that would be square root of 1e9, which fits in our complexity. And we can also do what for the cubes, right? 1 8 27 64 k cube. So in that case, k would be less than equals to cubic root of n, which is even faster. So this is approximately, let's say, 1e4, like I think 3e4, and this is just 1e3. So as you can see, the overall time complexity, if we first of all find all the square roots and then all the perfect squares and then all the perfect cubes, time complexity remains square root of n because it is root n plus cubic root of n. So that is just square root of n. Okay, so we can just do that, and we have to take care of the fact that there can be overlapping values. So we can store them in a set to distinguish. I mean, to just select the unique ones. So this is the implementation. I make a set and I have n, and then I first of all add all the squares, then I add all the cubes, and then I just print the size. So very trivial. I mean, at least for someone who has been doing CP for some time. If you didn't find it trivial, don't worry. After some time, it will become. So, third problem. Wrong addition. Okay, this was a little painful. Not really. So we have a broken way of addition. Okay, so we are given, let's say we have to add these two values 17236 and 3465. So this broken method of addition is like this. So obviously you can just add 0 here, it doesn't matter. Now what you do is you add like normal. So 6 plus 5, now 6 plus 5 is 11. Usually what you do is carry, but here you don't carry, you just write whatever it is. So 6 plus 5 11, and then 6 plus 3 9, and then 4 plus 2 6, then 7 plus 3 10, and then 1 plus 0 is 1. So this is the final thing. So what we are given is we are given some value a, and we are given some sum s, and we want to say we want to find some value b such that a plus b is equals to s with this broken method. So how do you do this? Well, you can just simulate it. So how does the simulation go? Let's try to find out from this example only. So if you know 6, okay, if you know this 6 and you know this 1, you want to know what value will come here, right? Because we want to form this number, right? So you know 6 and you know 1. I mean, you know the entire of this, but I'm starting from right only. So as you know, since 1 is smaller than 6, that means something was added which made it exceed 9. So made it become 2-digit. So we can know that we want to add something to 6 which is of one single digit that makes the resultant single digit 1. So obviously 6 plus 5 will give us something here and then 1 here. So you can figure out that okay, 5 is here. Okay, so yeah, you know 5. Good. Then you go to here and you see, and as you can see, you know, this is also covered out. So let's move it. Now you have 6 and 3. Sorry, you have 3 and 9. Now 9 is greater than 3. So you know that 9 minus 3, which is 6. 6 must have been here for 9 to be formed. Then similarly 6 minus 2 is 4. And now 0 minus 7. Obviously again it is the previous case. So you get a 3 here. And 10 gets covered here. And then you have 1 and 1. So 0 can be here. So the simulation looks simple, right? You go from the right and you see, okay, so the rightmost of a, if it is less than or equals to the rightmost of sum, then we know simply by subtraction, like 9 minus 3 is equals to 6. Otherwise you have to consider the 2 digits here. Okay, so let's say for example this was 8 and this was 9. Then you know that 9 must have been here for it to become 8. But there is one edge case. For in that case, this must be 18. But here it is 68. So whenever you are taking two digits of s, you have to make sure that the digit at once is 1. If it's anything else, we cannot do it. Okay, I think this much was somewhat easy to come up, but the implementation was slightly difficult. So let's have a look at the implementation. So first of all, you take the input, obviously A and S, and B is our result. Now what I'm doing here, first of all, okay, so this is the actual algorithm. So obviously S and A, okay, so in this algorithm what I'm doing is I'm removing every time I'm processing something. Let's say I have processed this much, okay, let's say I've processed 6 and 11, then I remove them from the string. So that is why I have this check that both of them exist. So I take the last value from string S, and it is a character, that is why I have to subtract 0 from it. So character 7 has some SI value, let's say 237. So to get 7 from this you have to subtract 0, because this will have 230, because in ASCII code or whatever code this uses, these values are consecutive. So anyways, here we are, and we take out the last elements from S and A, and then obviously remove them. And then what I check is, first of all, what I check is that if S is less than A, then that means I need one more from S. However, if S is empty now, then that means it is impossible to form B, so return out. Otherwise, then again I check if S is less than A, because, and now in this case S had something in it. So like I said here, that the value previous to it must be 1. It cannot be anything else. So I'm checking that S dot back is 1, and if it is not the case, then I return -1. Otherwise I increase the value. So I can just do si plus equals to 10 here. Don't worry about it, because I know that if it was like this, right, something something, this is A, this is S, and I remove first of all 6 and 1 here, and then I check that the value next to it is also 1, because this was less than this. And now that I've checked that this is 1, I know that I'm adding 10 only, and then I remove this as well from S, and this is also removed, and then I form the string B. So what comes in B? 11 minus 6, so 5, right? So 5, and it keeps getting added on the left side. So whatever is here, I keep adding to the left side. So that is why I'm doing B plus equals to whatever value is here plus B. And now in the end I'm checking if A still has something in it. Okay, if A still has something in it, but S doesn't have, because if A has something, then S doesn't have in it because of this condition. So then that means that A was somewhat less than S, sorry, greater than S, in a sense. So in that case also -1. Otherwise what we are doing here is, since now A is empty but S can have some things, right? So let's say A was 1 2 3 and S was 4 5 6 7. So in this case 4 minus 3 1, 5 minus 2 3, 6 minus 1 4. This is not complete, right? Because this is 0 here, so we want to add the remaining S as well. So so B equals to S plus B, again add it on the left side. And then what can happen is that like in this case 1 minus 1, we might be adding 0 on the left side. So first of all I reverse it, and then I remove all the zeros, and then I reverse it again. This is just a way to remove all the zeros in the front, and then I print B. So yeah, that was problem C. Okay, so problem D. So this guy has n friends. Okay, so there are n friends, let's call them f1, f2, f3 up to f of n. friend n basically, and there are m shops. Okay, so shop 1, shop 2, shop 3, shop 4, and shop m. Now what we want to do is we want to select at maximum n minus 1 shop and buy each of these friends a gift from that shop. Okay, and we know what is the happiness value. Let's call it a is for ith friend getting a gift from j's shop. So aij is the happiness we sorry, the ith friend gets from a gift at j's store. So what we want to do is, let's say friend 1 got a gift value of x1, this guy got x2, and so on, xn. Then we, whatever is the minimum value among them, let's say x5, okay, we want this minimum value to be maximum. So we want to keep all the friends as happy as possible. So we just want whichever friend is the least happy to be maximum possible. So what we have to do, okay, so the input format is a little different. The input format is like shops are here and friends are here, but I'll be explaining it in this way, and then we can just assume we can just change how the input is, because it is easier to explain this way. So for each friend we know how much happiness he get if he gets a gift from shop I or shop J. So now we want to maximize the minimum happiness that any friend gets. There is another constraint that we only can use n minus 1 shops. Now let's try to solve it first without this constraint. So how to do it? So, well, there can be probably a greedy solution, but notice that if all the friends get some gift with greater than equals to x value, right, which is let's say 5, okay, so if all friends get gift of happiness greater than equals to 5, then that means all the friends also get gift which is greater than equals to 3, which is greater than equals to 1 or 2. So basically, if you can check that is gift of happiness 5 is possible, then you don't have to check for all of them. What does this imply? Binary search. So let's see how we can binary search. So the gift, the answer, which was let's say minimum happiness, right? So the minimum happiness can vary from let's say 0 to infinity. Now it actually varies from whatever the minimum value is in the matrix and what is the maximum value. Maximum value is probably not possible in most cases, but maybe. Anyways, so this is the range, and now let's say we calculate that yeah, it is possible for 100 happiness, then we don't have to check for here, we'll just have to check here. So binary search obviously. Now let's see how we'll do it. So how can we check if some happiness x is possible to be delivered? By deliver I mean all friends get at least x happiness. And remember, right now there is no constraint that n minus 1 shops are only allowed. We can use n shops. So what I will do, right, is I'll iterate for ith friend through all the shops, and if any of these shop give more than or equals to x value of happiness, then this friend can be satisfied. Then similarly for friend 2, friend 3, friend 4 up to friend n. And if it remains true for all of them, then that means all of them got greater than equals to x or can get. So x is possible, and if x is possible, then search space reduces to x plus 1 to infinity or whatever the upper bound is, right? However, now we have another constraint, and that is only n minus 1 shops are allowed. Now we are using this, and it is very simple actually. So notice that only one shop. So we were able to, get the best possible outcome with just n shops because there are only n friends. But with n minus one shop, we may not get it. However, notice that we just need one more shop. We just need one shop to satisfy more than one person, right? Because let's say uh, some shop si1 satisfied this guy, si2 for this, si3 for this, and then si of n for this. So if any of these shop is equal, then we are using n minus 1 shops, right? So we just have to keep a track of what are the shops that are being used currently, and if any person for which happiness is greater than equals to x for some shop j, and this j exists in our set of the shops used, then these two friends can use single shop, and then we will be able to get x. However, if that doesn't happen, then that means x is not possible. So that was the algorithm or the idea. Now let's have a look at the implementation. So integer n m. So like I said, right? So I explained it with n in this dimension and m in this dimension, but who is the author? I hate him because what they have done is they've inverted it. So basically it's like shop 1, shop 2, shop m, and then friend 1, friend 2, friend n. So this is how we are getting input. And now, so we have to take input like that. That is why I'm taking m first and then n. And the matrix is also like m times n. So m in this direction and in this direction. Then I'm taking input by this line. Now if you don't know how this works, you can check out my template video. I just made it. And then I have the binary search. Okay. So low is 0, high is infinity. Infinity is a very big number in this case. 2e18. Now, and answer is 0. So I do binary search, I get the mid. And so I have the chosen shops here. And then I have two variables, can and can2. So can represents, can it be done for n shops, okay? And then can2 represents, can this be done for n minus 1 shops? So what I do here is I iterate for every shop. So shop is in j dimension. Sorry, for every friend, and friend is in j dimension, which is this, the column. And I'm setting can false, and if any of the shop happiness is greater than equals to mid, then can is equals to true for this row, and I basically do it for every row. And if at any row it stays false, then that means it is not possible. And I also do one more thing. I add this I value, which is the shop number, in the chosen shop set. And anytime I use a shop which has already been used, then that means that n minus 1 condition is also fulfilled. So if both conditions are fulfilled, answer is equals to at least mid, and low becomes mid plus 1. So basically I was trying mid. If this is done, then third space goes here. So mid plus 1 to high. Otherwise high goes to mid minus 1. So somewhat here. And then I just print the answer after the binary search. Okay, so problem E. So this was another implementational hell problem. I mean, not that bad, but okay. So we have an array E, right? And the numbers are non-negative, so 0 to infinity. Well, actually they go from 0 to n. And what we want to do is for every value x, okay, x goes from 0 to n, we want to tell if we can do some operations on array A such that after these operations the max of array A becomes x, and we want to find the minimum number of operations. So for example, let's say the array was this and x is 2, okay, and x is 2. So what we can, and what an operation is like, in an operation we can pick a number at some index and increase it by 1, okay. So choose some value I and then ai plus plus. So to get max of value 2, if you don't know what max is, max is basically, let's say I have a set 1 2 5 0 3 of values, then it is the smallest value, smallest non-negative value that doesn't occur in this set. So 0 occurs, 1 occurs, 2 occurs, 3 occurs, 4 doesn't. So 4 is the max. So that was a quick explanation of max. Well, I figure if you reached this problem, you can read the definition of max yourself. Anyhow, x is 2. So what we can do is, we can keep this 0 because we want 1 0, increment it by 1. So operation is 1 now, and this is 1. And but we don't want this to be 2, so increment it by 1 and it becomes 3. Okay, so this becomes 3. And our final array is 0 1 3 with operations done 2, and its max is, that's right, 2. So we just want to tell what is the minimum number of operations we have to do such that we can get the max of x for every x from 0 to n. So let's try to see what the max for, first of all, let's take some example. 4 6, this one, 4 6 2 3 5 0 5. So 4 6 2 3 5 0 5. So let's start. The max, first of all, we want 0. If we want the max to be 0, then what we want is, we don't want any 0 to be there, right? So we will increment every 0. So I'll increment this 0, I'll make this 1, and then, as we know, only 0 is missing, only the so we take the first, right? So let's say we have a set 2 3, its max is also 0 because while 0 and 1 both are missing, we only take the minimum. So in this case, since I have incremented all zeros, the max will be 0 now, and so answer for this is 1. Let's take x is equals to 1. So for 1, we don't have a 1 here. Okay, this is a bad example. Let's take 40104. So I'm taking example because it will be easier to understand that way. 40104. For x is equals to 0, we want to increase all the zeros, right? So we increase this and increase this, and finally answer is 2. Now for x is equals to 1, we want zeros to be there, but we don't want 1 to be there. So we have zeros, but we don't want 1, so we just increment 1 and answer is 1. For x is equals to 2, we have both 0 and 1, so we don't increment anything and answer is 0. For 3, however, for x is equals to 3, we increment 0. No. So we have 0, that's good. We have 1 as well, but we want 2 as well, otherwise our max will remain 2. So we'll have to increment 0 to 2 or 1 to 2, right? but if I increment 1 to 2, I'll have to increment 0 to 1 as well. So either I can increment this 0 two times, right? So either I can increment this 0 two times, or I can increment this once and this once. So both works. Let's do this, and then answer is 2. And then for 4, similarly, for 4, we want to increment. So for 4, as you can see, we have 0, right? We have 1. By incrementing this 2 times, we also have 2, but we don't have 3, and we cannot get 3 because to get 3, we want something less than equals to that. Since we cannot get 3, the answer is -1. Now we have to increment 4, but the thing is, the final set would become 0, 1, 2, 5, 5. There's still 3 missing, and we cannot get that. So that is why -1. So this covers a lot of cases, and as you can see, at every step, so obviously you see how to do it in n square, right? It will be trivial, just simulate it. But how to do it in O of n or O of n log n, because n is pretty big. So for every step, we have two portions. One is, let's say we are calculating for x is for some x, right? So if we are calculating for some x, we want the number of operations required to get all the values from 0 to x minus 1 to be covered. And then we want to increment all the values that are x, so frequency of x. This is what we want to do. And at any point of time, if this is not possible, the first part, then answer becomes -1. And if you see, even if we try to check for the further values, the answer will remain -1, because whatever value is missing here, right, will still keep on missing for any x greater than this current x. Reason being, whatever so whatever extra values we get to play with, right? So let's say I'm currently at x. I get to play with all the values from 0 to x minus 1. Anything greater than x cannot be used in any way, and x has to be incremented no matter what. So since I won't get any extra value in this range to play with, I won't be able to cover all of them. So even if I'm able to, at some point y, cover x to y, I still would be missing a hole here, somewhere here. Okay. So I'll still be missing something here. So let's say this value. So that is why once I get a -1, -1 keeps going on. So how to implement it? The implementation is like this. So I take input A, then I have a frequency array, and then I have a set which is the remaining values. Now this is slightly overkill of an implementation, but I don't have anything else. So I have a remaining set. So these are the values that I need to fill in. Okay, the values that I need to fill in, and I have a have value, which values I have, which I can use to fill in. For example, in case of 2, I had an extra 0, right? So I had an extra 0. This was in my extra, right? And I wanted to fill in, sorry, for x equals to 3, I had an extra 0. So 0 and 1 were done, but this was extra. And I wanted to fill in 2. So I was incrementing 0 to 2. So that's what I'm keeping track of. What are the remaining ones and what I have. And then this sum is the sum of operations to fill 0 to x minus 1. And then I have the skip variable. Basically, whenever I get -1, I just say skip equals to true. And every time I have to skip, see out -1, continue. So obviously I'm iterating from 0 to n. And then the answer at every step is whatever 0 to x minus 1 is operations are, and then the frequency of I, because we have to increment that. And now the thing is, however, if whatever this operation is, But if there is some remaining value, right? If there was some remaining value from 0 to x minus 1, then in that case answer becomes negative 1. Skips gets true. I print the answer, and this is basically useless after that. But let's see what I'm doing here. So every time this value, current value, is not in the array, right? Then that means, what that means is that this is a remaining value. This is something that I have to fill in. Otherwise, what I do is, first of all, I keep one of these value for the current thing, because see, I had two zeros here, so I had to leave 1 0 for filling in 0, right? And the other ones I push in my have array. Basically, the values I have at my disposal to fill in the remaining values. And then while there is something remaining and while I have something to fill it in, what I do is, first of all, I check that if any, so have is sorted by nature, right? So what I'm doing here is, while have is, something, while it has some size and its last value is greater than the last value of remaining, I just pop it back. And after that, I'm just doing a safety check here. After that, I'm getting the last value from the remaining and the last value from have. And basically, it's like if I have remaining values like 4 and 3 is remaining, and in my have I had two zeros. Okay, so I'm storing them like this. So I had two zeros. Oh, oops. What am I doing? So if I had two zeros and three ones extra, so what I do is, I use the last value to use it, to fill it. So basically I use 1 to first of all fill 4 and then 1 to fill in 3. Now it could have been like, okay, this is very glitchy. So it could have been like this, that I had 0 here, that I would use 0 to fill this. Okay, so this way this is optimal filling, and I add that to the sum, and that's it. So to formulate this implementation, so I just explained you what the implementation was, but the key to formulating this implementation was this idea, at least to me, that I'm storing two values. First is the number of operations to fill in 0 to x minus 1, and then the number of values here, and after that I do the filling, which I could do by having two sets, one the remaining ones and one the ones I already have that I can use to fill in. So yeah, and after that I would just print a new line, and that is it. Sorry if I sounded sick. Yes, I am a little bit sick today, for a few days actually. Sorry for that. But that being said, this was the editorial. I probably could have solved F or G, I don't know, but I had to make the video, man. Anything for the views. That being said, leave a like, subscribe. Doesn't matter if you liked it or not. And bye.